A sample data set has been provided for the purpose of practicing backscattering analysis. It is called void.dat. It already has a source receiver configuration encoded. That's why it has this SR appended in its file name. It has total 50 records of 24 channel acquisition for each record, and it is basically roll-along acquisition. And this line indicates the location of that modeled subsurface void or tunnel. It was located at this 44-meter location along the survey line. And these are 3 selected records, the first one and the middle one and the last one. And none of these records shows any indication of backscattering feature, which will become obvious on the final backscattering analysis map. This is a processing flowchart for backscattering analysis. First, you have to prepare a seismic dataset with the source receiver configuration encoded. Then you have to prepare dispersion curves. You can either prepare one dispersion curve that can represent average dispersion curve for the entire dataset, or you can prepare multiple dispersion curves obtained from different locations along the survey line. Then these dispersion curves will be applied to this seismic data, which will go through this analysis, which will generate this BSA section at the end. I'm going to demonstrate how to generate backscattering analysis map by using the sample dataset called void.sr.dat. First, I have to prepare a dispersion curve. Rather than generating all the dispersion curves for all 50 individual records included in the sample data, I'm going to generate one average dispersion curve by processing all those 50 records included in that sample data. For that, first go to Process and then Dispersion Analysis. And then I choose this void.sr.dat, and then this is gonna generate dispersion images for all those 50 records. So run. Now it's ready to move on to next step, which is extraction of dispersion curves. So I click yes. And now I have all 50 dispersion images here. So rather than going through each individual dispersion image and extract one dispersion curve from each image, I'm going to stack all these 50 dispersion images together and then extract one dispersion curve from that stacked image. And for that, I select Multi-OT tab here and then click Stack. Specify output file name for that stacked dispersion image file and click yes. And now it asks me if I want to replace current dispersion image dataset with the new stacked image data. I click yes. Now there is only one dispersion image, so I'm going to extract one dispersion curve from this stacked image, and I first change the scale of this display. To change the scale, you click the axis, and then it will show this dialog in which I specify maximum and minimum and also increment. And I specify here, because the modeling used 50 Hz as the highest frequency, there is almost no data here. This is a computational artifact, so I click here, and I'm going to display only up to 50 Hz, like this. And then probably for the purpose of aiding the scale, I just overlap the grids. And then go to dispersion analysis tab here, and then click bounds and set the new bounds here like this, and then extract, and I'm going to exclude this one and then save. Now it asks me if I want to move on to the next step, which will be inversion. I'm not going to use this dispersion curve to generate 1D velocity profile. So I click no. Then the dispersion curve is ready. Now I go for process and backscattering analysis here. And then I import that void sr.dat. And here I specify dispersion. So this is the dispersion curve which I just generated. Then I click output and then run BSA. And output is ready, and I'm going to display it. So this is the backscattering analysis map. I can change the scale, go here, and then I'm going to display only the top 1000 millisecond portion. And this is the backscattering from this location, which is 44 meter. And to emphasize this backscattering feature, we can actually filter this horizontal event. For that, go to process and then press down this filter button and then double click, and it shows this dialog. There I choose horizontal event, and this shows the default parameter for that filtering. 5 is usually sufficient, and then click OK. So it filtered horizontal events a lot. That's why this backscattering feature has been emphasized. Now I'm going to demonstrate how to evaluate depth to that detected void. First, I have to display that backscattering analysis map. Go to display and choose the seismic data, and this is the output from the backscattering analysis. And then it displays like this, and I choose the top half of the display. First, I go to process and choose filter, and then double click. I apply bandpath filtering of 10, 20, 20, and 30. So this is basically a very narrow banded bandpath filtering centered at 20 Hz. I apply it. I still see very strong backscattering. And I go back to original raw data here, and then filter again, this time with the higher center frequency, which is 20, 30, 30, and 40. And it still shows this very strong backscattering feature. And then now I'm going to apply higher bandpass filtering centered at 50 Hz. So applying now 40, 50, 50, and 60. And it's almost gone. And then I close this one and then display that analyze the dispersion curve, which is this one. And there I see at 50 Hz phase velocity is almost 150 meters per second. So it gives the wavelength at this 50 Hz is about 3 meters, which means the top of the void is deeper than at least 3 meters.